The project for this weekend was to explore a form of wireless communication, and for this project I chose to use infrared, or IR for short, to wirelessly control the Moorland bar graph. Here, individual bits can be turned on and off, the sequence of bits can be shifted left or right, the binary number can increment up or down, and pressing the play button enables a scrolling animation which can change direction. Pressing the play button again disables the scrolling. The power button turns off and on the display while the stop button resets the binary value to 0. While scrolling, regular functions like turning off and on individual bits can still be used. Originally, I'd planned to control Hugo Reed's Matrix Made Easy with IR, however the readings were very faulty, and I was unable to control it even when switching to hardware SPI. And after a couple of days of trying to fix the problem to no avail, I decided to step down to the much simpler Moorland bar graph. The parts list for this project is very simple and does not require a breadboard. Infrared is a type of wavelength with a frequency just lower than visible light, therefore it is invisible to the human eye and is not perceived. A lot of cameras, however, are actually able to visually detect this wavelength as their silicon-based sensor absorbs near and direct infrared signals. TVs and air conditioners use this type of wavelength for control using a transmitter diode, usually in the form of a remote, and a receiver diode picking up those signals. Signals from the transmitter are modulated, most commonly at 38 kHz, to differentiate between the remote signal and ambient IR. The receiver then demodulates the signal into a binary waveform and is then read by a microcontroller to ultimately perform a certain function. Different buttons on the remote send out a unique series of highs and lows to distinguish between buttons for performing a variety of activities. The process of controlling the Moorland bar graph is more or less the same. IR codes from the remote are picked up and demodulated by the Sharp receiver, and the bit stream from the output pin is read by the ATmega. Code from the sketch decodes the stream to form a unique IR code using Ken Sheriff's IR remote library. Holding down any button, however, will produce uniform repeat codes. If statements then compare the received IR code to the predetermined IR code, and if they match, the value is altered in some manner. For example, if the stop button is pressed, the ATmega will match that IR code with the stop button IR code, and the value will reset to 0. The same goes for turning on and off individual bits. Here, a for loop checks IR codes corresponding to the number pad 0 to 7 on the remote, and if one of the number codes is detected from pressing one of the numbers, it checks the state of the specific bit number and reverses the state. This technique of if statements is used for the rest of the button functions. There's probably an alternative way to more streamlined and cleaner code. However, with most of my time being used up to control the Matrix Made Easy using IR, I couldn't think of a better way. Once done checking the received code, the value is finally displayed on the bar graph using the much faster, hard-coded UNO SPI pins to control the 595 shift register and output the value in binary. And so, by implementing and exploring IR to control a simple bar graph, it has taught me the basics of how to effectively utilize this new form of communication for more complex and fancier projects in the future.